that tonight. We are now going to be talking about chemical bonding 3. Today we'll be talking about what are called bond characteristics and molecular polarity. So our quote of the day is from Bobby Taylor. A dude could jump off a mountain and not hurt himself because he did brace himself and knew something about the levels of gravity and polarity. Now, hopefully by the end of today you won't speak like Bobby Taylor. And you will know some things about polarity. So, if you look right up here, we have 3 burettes. In these burettes, we're putting different molecules. This first burette here, I happen to have water put into the burette. The second burette has hexane. Just pour it in here, make it easy. And the last one has isopropyl alcohol or isopropanol, depending on your decision to name it as such. Now, first thing you want to notice is looking at these molecules. What is similar about all 3 molecules? Got hydrogen, they're covalent. Very good. What else? Okay, they all happen to be clear and colorless. Alright? So for the first demonstration, what we are going to look at is hexane. So for hexane, what we're going to do is we're going to take a charged wand, this device here. If you take this device and rub it with a piece of silk, it becomes charged. We're going to take the hexane and open the burette and see what happens. Well, it looks like I already made a mess with water. Let's do water first. So, if you want to come up where you can see better. So, if you look up here. Okay, place the charge wand next to it. You get a good result for Kevin.
No, nobody's spitting on you.
There's so many pickpockets. Oh, kind of missing. There you go.
That's magical.
Come on, guys. It's not like Hey, brother peeves. Don't forget peeves. So much information. Alright. Now, the next one here, we'll turn the water off. Next one is hexane. It's already tilted. You got to notice that to begin with. It happens to be burette. It's hexane. Alright, so let's test the last one here. Hopefully we can get lined up on this again. So this one is isopropyl alcohol. Try to reach over, see if I can reach it. Now, looks like magic, but all it is chemistry. Yeah, this right here is not something you want to inhale.
Okay.
So, but you will notice one thing about hexane is it does not go towards the charged one.
Well, water has
Yeah,
no
oh.
too.
You're an isopropyl alcohol.
Hexane doesn't have O. There it is.
All right. With our demonstration, what did the hexane do with the charged one? Nothing. Nothing. All right, what about the isopropanol? Okay. All right, went towards it. Very good. That's also called attracted. Water. What did the water do? Okay, it went towards it as well. Okay. All right. Now, this here is a picture of the demonstration. You have a burette. Water happens to go towards the charged one. So the question is, why do these two attract, and why does the hexane do absolutely nothing, like some of my students in that side of the room? Oh, wait, you're talking. Oh, I'm sorry. Did I interrupt you? You too busy emailing someone right now? Did I interrupt you guys over here? I heard some noise over there, like you were talking to yourself or someone else. So I apologize if I'm interrupting your personal time. Please go outside if you need personal time. Okay, it's a little bit better. I can actually hear that you're not talking. That's good. So why is it? What's going on? What's happening in this case? We've got hexane, we've got isopropanol, we've got water. What could be happening? Yes, what do you think?
Water is polar, and I'm guessing isopropanol is too.
Okay, so water you think is polar, and you're guessing that isopropanol is polar as well. Okay, so if they're polar, maybe they get attracted. Yeah?
Well, the hexane is only made out of carbon is hydrogen, so that's not polar. It's just like the difference in electronegativity is big enough.
All right, so the difference in electronegativity between C and H is not big enough. So the electronegativity difference is too small. So you're saying it's going to not be polar. Okay, thank you. Any other ideas? What do you think is going on? Yes, sir. Okay. All right, hexane is a ring, so it's equally distributed. Okay, since it's equally distributed, it's not going towards the charged one. Yes, sir.
Oxygen causes polarity to be more amplified.
Okay, so oxygen. We got oxygen here and oxygen here. So this is what causes the polarity to be more amplified. Now, based on what we know about things in general, polarity is what we're going to look at today specifically. Now, one other cool thing you can do with hexane is if you place it on a piece of wax paper. Normally, if you place a drop of water on wax paper, it beads up like a drop. If you put hexane on a piece of wax paper, it goes like this. Spreads out. It does not bead up like a drop. Maybe we'll look at this after our lecture to see what happens. Okay. The hexane does not go towards the charged one. The isopropanol and water do. The reason water goes towards the charged one is because water molecules have a slight negative end and a slight positive end. This is what is called polarity. The reason they have a slight negative and positive end is due to the electronegativity difference. The charged one has either negative or a positive charge. I could not tell you which in that case, but it will attract the opposite side of the water molecules. Now, when all these water molecules turn and the positive faces the negative, you'll notice that all the oxygens have a negative charge, so they attract more water molecules. And this is what causes the water to attract to itself and to attract to a charged one. This is why if you have a piece of glass, this is why the water curves up on the sides of it, because the meniscus, it curves up because it sticks to the outside of the glass.
Isn't that how MRIs work?
MRIs, they do work based on some of these properties, although what they mainly do is they don't work directly with all the polar molecules, they have to differentiate between things that are normally polar, and what they do is they create a magnetic field that causes other molecules to change and create what's called a temporary dipole. So it's not exactly this, but it does do, it's the same principle behind it, yes. It's just not, you usually don't want to know exactly where the water molecules are, but you cause that vibration or rotation, and that allows you to visualize what's going on in the body. So MRIs are a little more complex, but they do involve the same basic polarity principle. Much of biochemistry, for those of you that are interested in going into medicine, involves polarity. It's an amazing, amazing thing that happens in the body, and almost all biochemical reactions involve some sort of polarity change, and it has to do with how the molecule, especially water, relates. Yeah?
So is this why water wasn't attracted on one side, but it was on the other?
The interesting thing about water is if I put the, it is not why that happened. The reason that happened is because I held this. And I grounded the charge by accident. So, if we did it again on the other side of the water molecule, we should be able to, or the water, we should be able to get the same results. We should be able to shoot it off to the side if I don't make a mistake. Because the thing about the water, we can spin it around this way, that way, and then we'll shoot it off the table. And that has to do with water's polarity, and it's an extremely polar molecule. Now, a single water molecule looks like this here with the positive and negative ends. These little signs here are the Greek symbol lowercase delta, which means slight charge. A polar molecule that is put into space near charge 1 will be attracted to the charged 1. Now, bond polarity. Which molecules are attracted to a charged 1? If we had fluorine, F2, you'll notice these diagrams are meant to show how the electrons are spaced out. It's called an electron density diagram. This one here shows that the electrons are shared equally. This is what is called nonpolar covalent. Molecules like HF, where the H has a lower electron density and the F has a higher electron density, are called polar covalent, and they get attracted to a charged 1. Lithium fluoride, which is an ionic molecule here, the positive and negative are completely separated. There's a transfer of electrons, and so if you had a negative wand and you were in a solution, it's possible the positive lithiums could attract to it, and if it was positive, you could have the negatives attract to it. But the challenge with an ionic substance is the whole thing doesn't go to one place. It's only here that it will be attracted or repelled, attracted to the charge 1, depending on what the charge 1's charge is. Now, if we look at these elements here, we should be able to answer the following question about these elements. Which atom has the greatest tendency to attract shared electrons? So I'm going to give you 1 minute. This is a multiple choice quiz. 1 minute to try to come up with an answer. Just need to choose one and explain why. You have 1 minute to think about it. Ready, set, go. All right, ladies and gentlemen. At this time, we're going to vote. All you got to do is raise your hand when I say the correct letter, whatever letter you think it is. All right? D. D is in dog. B is in bat. A is in audible. C is in Carmichael. Carmichael. All right. So, some people said D, some people said B. Those are the most logical, best choices. Why is A not so good? Okay. All right, lithium. What's up with lithium? Okay, one, it's a metal. Okay. It's an alkali metal. All right. What else about it?
It only has one valence electron.
Got one valence electron. Okay, so it doesn't want to share. What does it want to do? Okay, it wants to lose it. So lithium out of the question. Good job. What about aluminum? It's chubby. All right, it's large. Okay, so aluminum is large, just like lithium. Very good. 1.52, 1.43. It's also a metal. Size, yep. Radius right there. Yeah, 1.43 angstroms. You're like, okay, that makes a difference. Which one is bigger, fluorine or chlorine? Okay, chlorine is bigger. Now in chlorine, you'll notice you got 2 electrons here, and then you have 8 in here. What also happens if you have electrons on the inside shells? Was it? Shielding. So in chlorine, there is actually shielding. Now there is a positive 17 charge. So you would think, well, wait a minute. If you had an electron out here, wouldn't it be attracted to the nucleus? Because it's got 17 charge, and this only has a +9. What would we have to calculate to know why fluorine is the best? Okay, ZF. That would tell us for sure why, if we needed a number to prove it. But fluorine is the best, and this is due to Coulomb's law, that the force is equal to a constant times the charge over r squared, to the distance, the radius here. So it has to do with the 3-dimensional space. So fluorine does attract electrons most to itself, and it is also, what we already know, which is a good way of knowing this, is it has the greatest electronegativity. So you might not have even looked at Coulomb's law, but that is why it has the greatest electronegativity, is due to the fact that the charge distance is much smaller, the radius is much smaller, and the charge itself is not as shielded. Yes?
So are atoms that have like a higher ZF and are like smaller and such, do they have higher electronegativity?
Tends to be the case, yes. Yeah. So electronegativity is the tendency of an atom to attract a shared electron pair. It increases across and decreases down. So this is another way of visualizing the electronegativity trend. Which atom do we know has the smallest electronegativity? Francium down here. Sometimes it's called electropositive. What? It's because it tends to give up those electrons. And then our fluorine is up here, the electronegative. Okay? Now, what the electronegativity does is gives us what's called a bond dipole. If we have this molecule here, HCl, here's the H and here's the Cl. Okay? The strength of the bond is determined by the electronegativity difference. So, which one has a greater electronegativity, Cl or H? Okay, the Cl does. So that's why it is a partial negative charge. The H is a partial positive because, again, its electronegativity is not as great. This arrow is what is called a dipole moment. This side of the arrow has a cross on it or a plus sign. That's the positive end. This side is the negative end. It always points towards the negative end of the molecule. Now, this particular molecule has a particular what's called bond strength. This is the bond polarization that induces a partial ionic character to the HCl bond. This makes the bond stronger. So it's not sharing equally. To see this clearly, here's a little comment. Here you have an H, here you have a Cl. Okay, are they sharing that ice cream equally? No. Now, the ice cream has how many scoops on it? 2. How many electrons is HCl sharing? 2. The 2 scoops of ice cream each represent an electron. Now, what does the cone represent? We call that a bond. So they're not sharing equally. Cl's taking it, H is definitely not. And because that unequal sharing, the electrons tend to be located closer to the Cl. And this is what's shown by this density diagram. Does that make sense? Okay? Now, if we look at a bond, a single bond, it has a dipole, HCl. If you look at these pictures here, this here is our HCl. This has a bond to dipole because there's only one bond here. When you have more than one bond, you have to think about the whole entire molecule. So here's H2O. H2O, are the O and H sharing equally? Nope, they're not sharing equally. The electrons tend to be closer to the O in these bonds. And so what happens is you have polar bonds, and the entire molecule ends up being what? Polar. The arrow, the dipole points towards the O. So if you add up both of these vectors, you would get the total polarity of the molecule. In this one here, CO2, there's an O, there's an O. How many ice cream scoops are in each of these? 4. That means it's what type of bond? Double bond. So a double bond here and a double bond here. CO2 has 2 electron domains. What's its shape going to be? Straight or linear? And if it's in a straight line and one is pulling this way and one is pulling this way, what happens, physics people? One, it wouldn't move if it was physically direction. If you have a force in this way, a force in this way, what's the net force going to be? 0. So they cancel each other out. Non-physics people. Right? Net force is 0. Now, if we look at polarity and shape, polar molecules are always attracted to a charged one. Water was attracted to a charged 1 because it has one end that is slightly negative, one end that is slightly positive. Chloromethane, would that be attracted to a charged 1?
Yeah.
Yep. Which end would be going towards the charged 1? It depends on what the charged 1 is charged with. Could be either side. It will stick to itself because of that property. It's really cool. So, chloromethane. If we look here at methane, methane is not attracted to a charged 1. Because the distribution of the electrons, the dipoles cancel out. Tetrachloromethane, 4 chlorines, 1 carbon. This is also non-polar because the chlorines cancel out, the dipoles cancel out in 3 dimensions. This is called a symmetrical shape. What's the shape of methane or tetrachloromethane? Tetrahedral. And that tetrahedral is a symmetrical shape which will cancel out if they're all the same. Acetylene, 2 carbons, 2 hydrogens. Why is that non-polar? Tell the person next to you. Alright, on this one here, you'll notice the carbon in the middle has more electronegativity. So there's going to be 1 dipole pointing this way, 1 dipole pointing this way. If they're both pointing the same direction with the same amount, what do? They cancel out. Okay? Since they cancel out, this is a symmetrical molecule. Acetylene is not going to be attracted to the charge 1. What about hexane? Was that attracted to the charge 1? No. So what would that be?
It would be like a
Would it be polar or non-polar? It's going to be non-polar. And hexane's actual structure, it's a larger molecule, but hexane's actual structure, let's see if I have room to draw this in here. Don't know if I left room for hexane. So hexane's structure here is C6. It's got 6 carbons. 1, 2, 3, 4, 5, 6. It happens to not be in a ring, unfortunately. But it's got hydrogens completely around it. Now, the interesting thing about hexane is it is non-polar because it's not attracted to a charged one. The reason it's non-polar is if you look at one of these C's here, what's the shape going to be around that C right there? A tetrahedral. And because that shape is a tetrahedral, what's the one going to be around this one? Tetrahedral. Yeah, so if you really tried to draw this out, it's a little very difficult to do, but you could try to draw it out like this. Oh, did I get that one? That's not a very good one. So, I'm not going to try to draw it. There we go. I don't have an eraser, so there we go. So all of these C's are tetrahedral. They're all like little tetrahedrons connected together. Okay, and all of these C's are connected together, and so this shape here is not a straight line, but because of all of those C's connected together, it is not polar or non-polar. And that's because there is no electronegativity difference, especially on the whole molecule, but every single tetrahedral, the dipoles all cancel out. Now, electronegativity is defined as the ability of an atom to attract towards itself the electrons in a chemical bond. So, which one of these two is more electronegative, the one on the left or the right?
Right.
The right, if red is a higher electron density. Okay, F is the highest electronegativity. Polar bonds are bonds where the electron density is not shared equally between the two bonded atoms. In polar bonds, there's a positive end and a negative end to the bond. This is referred to as a dipole. So if you have a polar bond, it has a dipole. If something has a dipole, it is polar, and vice versa. If we look at a polar covalent bond or polar bond, is a covalent bond with greater electron density around one of the two atoms. So in this case, fluorine has a greater electron density. Why? Why does fluorine have a greater electron density? Yeah? No. Good guess, but that's wrong. Unfortunately, it happens to be there are more electrons around it, but that would not be true. Yeah? Yeah? That is correct. Electronegativity is greater for fluorine. Okay, just because it has more electrons around it does not mean it will be the more electronegative element. If we had F and Cl, they both would have the same amount of electrons around it. But which one would attract the electrons more? F would. All right? So you got the electron-rich region and the electron-poor region. And shown in the Lewis dot structure, there's your HF. The F has a slight negative charge, the H has a slight positive charge. So that is a lowercase delta, which means slight charge. So here's our HF, again shown without the lone pairs around the F. The dipole goes in that direction because the F is negative and the H is positive. Now, looking at the dipole nature and the bond character, when electronegativity difference is 0, the bond type we get is called a covalent bond. Or some people even call it non-polar covalent, to be very specific. When the difference is intermediate, it's called a polar covalent bond. That means it has some ionic character to it. And when the electronegativity difference is really large, it's called ionic. Okay, that means there's not really any sharing going on. Sodium and chlorine. The sodium would lose that electron and chlorine would take it, just like in the ice cream picture. It would run away with it though. And sodium, in that case, would run after the chlorine trying to get the ice cream. The covalent character decreases and the ionic character increases as the electronegativity difference goes up. Now, the classification of bonds by differences in electronegativity. These are the numbers we have to use, or are most commonly used, to define a bond type. If there's no difference, it's called covalent. If the difference is greater than 2, it's called ionic. And if it's in between, it's called polar covalent. Now, you will see some debate around this 2 right here. We will be using 2 as our defining characteristic. There are some things that might be polar covalent that will be a little bit above 2. And this is where there can be difficulty, but we'll be using 2 for most of our problems we're looking at. As you increase the difference in electronegativity, it goes from covalent to polar covalent, sharing equally, not sharing so well, and transferring them completely. This here is a percent ionic character versus electronegativity difference. You can see the ones up here, like lithium fluoride, have the highest percent ionic character. Does it go to 100%? No. So even though lithium gives up its electron to fluorine, are they still kind of sharing a little bit? Yeah, so when we call it an ionic bond, it's not a complete transfer, even if you get up here at the top. Okay, if you look at something like this, HF. Okay, HF's kind of in the middle here. LII or LICL is up here, LIBR. So you can see there's a range, what's called a continuum. This is shown here by this picture of bond polarity. On the left, we have sodium chloride, hydrochloric acid, and chlorine gas. Why is chlorine gas nonpolar? Okay, same electronegativity. What are they doing with the electrons? Okay, sharing equally. All right? And so we see HCl, polar covalent, and ionic is NaCl. Is there still some sharing going on with the NaCl? Of course. Okay, it might be a lot less sharing than HCl and Cl2. This here is another way of representing the characteristics of bonds. This is called a bond triangle. It shows the relationship between ionic, covalent, and metallic, which was the one thing missing. This here is an actual bond triangle. It uses a couple different equations to give you a triangle with the data. It uses ionic and covalent percent character, and it also uses electronegativity differences. So you can see up here, the best or the most ionic one is cesium fluoride. The most metallic one is cesium, and the most covalent one is fluorine, based on this data here. So you can see as you go down, it becomes more covalent. Here it becomes more metallic as you go across. And you can see carbon here is kind of in between, right? It's in between the covalent side and the metallic side. And this is why elements in carbon's column tend to be called semi-metals or metalloids. So this is another way of trying to visualize the different characteristics of compounds. This particular diagram works really well for solids, but it is not something that we will use very often. Some chemistry classes in college will use this more. We will be using it not as much, but I wanted to show you that. So let's see if we can classify the following bonds. So in the next minute, please classify these 3 bonds. On your mark, get set, go.
One's gonna be taking up all of it.
All right, let's look and see. All right, looking at this here, we've got our periodic table with the metals over here and the non-metals over here. Most electronegative is up here with the fluorine. We look first at the CS and Cl. Cesium is 0.7 electronegativity. Cl is 3.0. So if we can subtract the two, we get what? Okay, 2.3. Difference of electronegativity, is it greater than 2?
Yes.
Yep, so this is called what? Ionic. Next one, H and S. Take the difference between the two. 0.4. Okay. And we're covalent. Okay, next one. HN. I'm sorry, NN in H2NN H2. Yep.
How do you know that cesium is 0 How do you get the where'd you get that from?
Electronegativity. Where you get that from is you can get that from an electronegativity chart. Look that up. That's one way to know. Yeah, you can't get it off the straight up periodic table. You can look at an electronegativity chart. You might be given the numbers, but not the charts. You don't have to memorize them. However, you should be able to look at it here. Okay, the big thing here is if you look here, you've got a metal here. Metals and non-metals usually have a large electronegativity difference. So if you have something that's way down here near francium and way up here near fluorine, the difference here is probably going to be very great. Metals and non-metals tend to form ionic bonds. So anytime you have a metal and a non-metal, it tends to form an ionic bond. Some of those ionic bonds will be more polar covalent in character, so it changes as you go closer to 2. But that is how you would find this information. H and S here are much closer together, because H is a non-metal, and S is a non-metal as well. So without the numbers, that's how I would determine it. Yeah, the pattern, the general trend. The next one, nitrogen. You got 2 nitrogens. They're going to have the same electronegativity, so their bond type is going to be what? Okay, covalent, or non-polar covalent if you had to choose that one as an option. Now, in molecules, the dipole moment is represented by the arrow. Dipole moment is the measure of the net molecular polarity, the overall pull of electrons towards one direction in a molecule. Dipole moments, as we said, are vectors. They are a measure of the separation of charge in units of debye. QR is the charge times the separation. So the distance times that charge. Yes, sir? Uh-huh.
So if it's like the same, it's just
Correct. Yep, exactly. If it's exactly the same, it's going to be covalent for sure. That's the unit. Capital D. Debye are just the measurement of the charge in units of debye instead of other. QR is how you calculate this. The charge times the separation. R is usually in radius. R is usually, the radius. And I'll show you how to calculate that next. Uh-huh. Uh-huh. Well, separation technique. The R is a little bit weird in this case. So if we look at polar molecules, to get the QR here, Q is the charge, and R is the distance between charges. Okay. 1 debye equals 3.36 times 10 to the negative 30th coulometers.
Why does it have like little piping? I thought the D
I'm sorry, the debis are the units you use.
Oh.
So you get this here, and then you'll be using the debi as the unit. Polar molecules have a permanent dipole moment. So if a molecule is polar, its dipole moment will stay the same. It doesn't matter what's happening to it. Okay? In an NMR machine, you're going to be altering the dipole moments of other molecules usually, not just the polar ones. HF molecules will align with an electric field. So if you put them into an electric field, they will arrange themselves according to that electric field. Yep.
For the previous slide, it says polar molecules have a permanent dipole moment. That means it's
That fixed
all.
number.
Oh, okay.
Yeah, so anytime you got water, it's got a specific dipole moment.
It will always be that.
Yep. So what happens with HF? If we put a magnetic field around the HF, here's the HF molecules floating around. We had a positive and negative charge. You'll notice the F's are always towards what side? Okay, towards the positive, and the H's are towards the negative. Yes?
Is that basically how NMR works, or?
It's basically how it works, correct. And then what they do is they switch these sides, and it causes all the molecules to go whoop, and they go whoop, and back and forth. And so that's basically, as we were saying before, that's part of the way it works. It also has the ability to create what are called partial dipoles, which are on molecules like nonpolar molecules, like nitrogen, for example. Not that you would have to. If you had a molecule in the body where you could distribute the electrons towards one side or the other, if you have a positive charge on here, the electrons could be pulled this way, and that could affect the other molecules next to it, even though they're all nonpolar. So you can do what's called an induced dipole. So, we'll look at that a little bit later. So let's look at dipole moments. Which molecules have a dipole moment? Dipole moment forms when all dipoles do not cancel each other completely. Any two-atom molecule with a polar bond. With three or more atoms, there are three considerations. First thing is there must be at least one dipole. There must be a polar bond. Second thing, there are significant strength differences among the dipoles. So there must be a difference among the dipoles in the molecule. And the third thing is the molecule has an asymmetrical geometry. So there are three things to consider. Any of these things could cause it to be have a dipole moment, a polar molecule. Yes?
What do you mean by significant strength differences amongst the dipoles?
So what this means is if you have, for example, if you have multiple atoms around a single central atom, and maybe you have different elements around that have different dipoles, then you're going to have significant strength differences.
Okay.
So basically, if the ones aren't all the same around the outside, you could have multiple things that have differences in polarity in the bonds, and that will change it.
So you're talking about like the central atom, and then around it there might be like H or.
Yeah, if you have an H and a Cl and an F, or if you have all three, you're going to have differences for sure.
Okay, so for sure if it's different, then it will have a dipole moment.
Correct. If they're all the same around the outside, it could be nonpolar. It could, if it's symmetrical. But we're looking at which ones are polar specifically. So let's look at this molecule here, BeCl2. This molecule here has a polar bond, BeCl, BeCl. Okay, which one is more electronegative, Be or Cl? Okay, the Cl is. So the dipoles would be going in this direction and that direction. The dipoles are pointing in opposite directions and they are equal in magnitude. So that means they do what? They cancel. That means the molecule has no dipole moment and is called a nonpolar molecule. And this works great for Be because Be doesn't have any lone pairs around it. Carbon dioxide, okay, its dipole is 0 debis. Carbon dioxide, is it going to be polar or nonpolar? Okay, nonpolar. HBEF. F and H are more electronegative than Be. So which direction does the dipoles go? Okay, they go out. but
But it's more oh, okay, I get it now.
which one is more electronegative?
That
The F is. The electrons will be closer to F, so it has a stronger dipole. And molecule is symmetrical, but dipole forces do not completely cancel out. So the electrons are going to be found more in this region here, than over here. They're going to be pulled towards the F in that direction. Molecule has a dipole moment and is polar. Okay, so is BF3 polar? So BF3, please draw the Lewis structure for BF3 very quickly. All right, time's up. All right, BF3. Okay, BF3 is a trigonal planar structure. It's got 3 electron domains. The electronegativity of F is much greater than B. Okay, they all have dipoles, but trigonal planar is a symmetrical shape. All dipoles completely cancel, so there is no dipole moment, and it is not polar. Are there any lone pairs around the B here? No. Got 3 electron domains, no lone pairs. Okay? So 3 electron domains means it can be trigonal planar. Let's look at CCl4. Think about CCl4. Is it going to be polar? The answer is yes or no. So, choose your answer just based on a hunch or a feeling or whatever else you want to do. Let's check it out. There's CCl4. What's the shape? Tetrahedral. Tetrahedral shape is a symmetrical shape. Cl is greater than C. The dipoles have equal strength. Tetrahedral is symmetrical. All dipoles completely cancel. No dipole moment. It is not polar. NH3. So first thing you can do is draw a Lewis structure, then determine its shape, then determine the electronegativity differences. All right, NH3, is it polar? That's its electron, that's its molecular shape with lone pairs. It's got a trigonal planar shape. H is less than N in terms of electronegativity. It does have dipoles, all going towards the N. There's a net dipole upward. It is trigonal pyramidal, and the trigonal pyramidal shape is called asymmetrical because it is not symmetrical. All dipoles are additive, and so when they add together, it means the entire molecule is polar. The resultant of adding together all the dipoles happens to be 1.47 debis. It is a polar molecule, known as ammonia. Now, some of you noticed something unique about ammonia that wasn't on the other ones so far. There is a lone pair. Now, oftentimes lone pairs are helpful, but not always. I do need to warn you. Lone pairs will not always give you the easy answer. Many times it works, but lone pairs are not the rule in chemistry. So there's ammonia. You see there's more electrons up here than down here. The net dipole is going upwards in this particular molecule. Yes?
why is that? Like why does the dipole moment increase going to the lone pairs?
It doesn't have to do with the lone pairs. It has to do with nitrogen in particular. Nitrogen versus hydrogen. Nitrogen has a greater electronegativity than hydrogen. So the electrons are moved towards this direction.
So if it was like
Okay, the lone pairs don't necessarily have anything to do with the fact that the electrons are pulled this way. They just are on this side of the molecule, and all of these sides have less electrons, so these are slightly positive because some electrons have moved. So the electron pairs are closer, 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 and here they're already there.
Okay.
So that's one way of thinking about it dimensionally. Although we can't really predict where the electrons are at any one time, that's another issue. Yeah?
So what would happen if you had O's instead of H's, like NO3 or
Let's look at
NO3?
that. NF3. Here's NF3. Instead of having H's, we got F's. Which one's more electronegative, N or F? F is. So which way would the dipoles be pointing? Okay, down in the three directions, and if you add them all up, that will be a net dipole pointing downwards. F is greater than N. It has dipoles. It's asymmetrical still. Dipoles do not cancel. It is polar. The resultant dipole is only 0.24 debye. A lot less than the NH3 was. So this molecule here has less of a dipole moment than NH3 does.
What was the other one?
The other one was 1.47 debye. It's just a way of comparing the polarity of an individual molecule. Yeah, I'm sorry, I stepped on ahead. Yeah?
Then how come for the NF3, the dipole for the is approaching the lone pairs? Shouldn't it be going
Yeah, I don't know why that dipole's there in the first place.
Which one? Okay,
This thing here, showing a dipole here,
yeah. Is that not?
it's not a dipole because it's not a bond. They might be showing that there's an electron charge in that area because electrons are here, there's two electrons. But
So would you say not to show that then?
I would not show it.
Okay.
I would not show it.
So only to make sure choosing the actual atoms.
Yes. Yeah, you only show dipoles for bonds. I do not show dipoles for lone pairs, although some people, would it be wrong? Depends who's grading your AP exam.
But then
Probably not.
that's not complete.
I know.
That'd be like
No, probably not. I wouldn't draw it. Yeah, I wouldn't draw it at all. It's not the best representation. Because dipoles are only showing bonds. So dipoles are only for bonds, and then a net dipole shows for the molecule. So this would be all you'd have to draw, the big one and the small one. So you wouldn't have to draw all the little ones. Okay. Does that make sense?
So you really actually only show the net.
Yes. Yeah, and chemists usually don't concern themselves too much with with adding them up either, although this is your resultant. Now, the reason why there is a larger net dipole here on the NH3, okay, is due to these three here pointing in the up direction, as well as the electronegativity change here due to these electrons. So the lone pairs do make a difference in terms of the number of electrons. There's more electrons in this location of space, and there's less electrons in this location because they're spread out. And you don't have the lone pair. So the lone pair does make a little bit of a difference in the resultant dipole. Now, water is interesting because water is even more polar because the O and the H's have dipole moments here. When you add those up, you get the net dipole of 1.85 debye. Okay? Water is an extremely polar molecule. And once again, the lone pairs, there's lots of electrons found here. All these electrons are pulled towards here. So you've got a very large negative charge in this region of the water molecule. Lone pair electrons do not make a molecule polar. This is the number one mistake. Number one mistake is people just assume it's got a lone pair, it's got to be polar. That is definitely not true. It's all about the shape. So you got to know the shape before you start guessing if it's polar or not. So here's a good example, ICl2 minus. Okay, ICl2, drawing the Lewis dot structure. It's got lone pairs. but it's not polar. Why not? Why isn't it? It is because the dipoles cancel out. It's also because all three of these are in the trigonal bipyramidal shape. And so they do not change the angle here. It's 180 degrees. The dipoles cancel. These three lone pairs do not affect the symmetry of the shape. So it's a linear molecule from a trigonal bipyramidal electron shape, electronic shape. So these three and those two. So you have the two chlorines on the top and the three lone pairs around it. So if we could draw this here, it's very hard to do, but there's our lone pairs are the yellow ones, our chlorines are the orange ones. So they'd be in a straight line. Difficult to visually show. I thought I had a picture of it. All right. What about CBr3F? Is it polar? Give you 5 seconds to decide. On the count of 3, say polar or non-polar. 1, 2, 3. They got dipoles. Tetrahedron is symmetrical. Dipoles do not completely cancel, so it is polar. Asymmetrical dipole forces make a molecule polar all the time. Yes? Uh-huh. Uh-huh. The thing about the fluorine is it pulls the electrons from all of these, so the electrons all get pulled in this direction here. So that is why it would be. You would think that the 3BRs would affect it more, but the fluorine wins. So. No, the amount does not affect it, only if you're trying to calculate the actual Debye amount, which we don't do very often.
So no matter what, if it's more electronegative,
It'll be towards that direction. Yep. Mm-hmm. Yes, sir.
So in general, they have like 3 different elements. There's tetrahedral, dipole,
Correct. Mm-hmm. Yeah, if you got things around a carbon, and one of them doesn't match, it's going to be polar. 2 of them don't match, it's still going to be polar. 3 of them don't match, still going to be polar. So, if they're not all the same around a tetrahedral, it's going to be polar. These, if this was Br, this was Br, this was F, and this was F, they would not cancel. Even though you're like, wait, they're evenly matched. No, they're not. Because the 3, it's not a crisscross. It's a tetrahedral. So that's a common mistake. You got to get asymmetrical dipole forces. Now, symmetrical molecules. We were talking about symmetrical molecules. It's good to know which ones are symmetrical because these could be non-polar if everything around the outside is the same. So, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar are all symmetrical molecules. Again, assuming all the x's around the outside are the same atom, or the same electronegativity difference, you're going to get non-polar molecules. Things that are asymmetrical. Yep. Yeah, you could have F, 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 and then a Cl. And boom, that's going to be polar now. The only, yeah. And it is to there is a chance you could mess around with the numbers and get 2 different elements that have the same electronegativity difference. And you would get a value really close to 0, and then you'd have chemists debating for years, is it polar or non-polar? But there's, yeah, but if the charged rod doesn't have enough charge to pull it, and there's not enough attraction. Yeah, there's a lot of debate in this area. For example, the 2.0 I told you, look at 3 different books, 3 different chemistry books, they'll all tell you a different number for ionic and covalent. That's because there's a gray area. Bonds are invented by humans, and there's lots of debate over how they function. Yes? No, they always attract. because the molecule will flip around so that it attracts. So that's the cool thing about polarity is they don't repel. If you have an individual charge, like in physics class, then you can repel all you want. But chemistry always attracts. All right, next thing, bent or V shape. These are all asymmetrical molecules. Some people like to remember the symmetrical ones. Some people like to remember the asymmetrical ones. So your bent or V shape, trigonal pyramidal, seesaw T-shape, and square pyramidal are all asymmetrical. They will always be polar, even if they have the same thing around them.
Wait, can you go back to the other slide? Oh.
Now, CH3Cl, is it going to be polar or non-polar? Okay, polar is correct. Very good. Now, we've looked at bonds. We've looked at how they connect together. Bonded atoms are more stable than singular atoms. So when they connect together with a bond, they're more stable. Forming bonds is an exothermic process. So if you make a bond, it releases energy. If you break a bond, remember? Requires energy to be added in. Okay, with the magnets. So, because of this, the bond dissociation energy is called delta H. The amount required to break a particular bond in 1 mole of a gaseous molecule is called the bond dissociation energy. The energy to break a particular bond. When hydrogens are coming together, if hydrogens are very far apart, okay, they start here, they come closer and closer together. If they're exactly 0.074 nanometers away, this is where a hydrogen-hydrogen will bond together. If you try to push the hydrogens too close together, here, the hydrogens, the positive protons are going to do what? Protons are going to repel each other. So you try to push it this way, it repels until it gets right here to this state. And this is its most stable state of a 0.074 nanometers. The energy here is too high for them to be close. The energy here is 0, they're too far away from each other. Here, this is a negative energy value, okay, a negative energy value, which is the most stable here for this bond length. So when you break that bond, you have to add energy. Watch this. You got to push it up the hill. You got to add energy to get it to break apart. You got to add enough energy so it's so far apart that it won't come back together. Hopefully, for a little while. Okay? To try to get them to collide together. If you get two hydrogens and you collide them together, you can try to make, if you have isotopes of hydrogen, you can try to make fusion, nuclear fusion. To do that, you got to go up this side of the ramp. And keep going up about 100 times. No, 1,000 times. Lots and lots of energy to get them to collide. That's why it's difficult to do nuclear fusion. So that here would be a picture of nuclear fusion there. You could get them to collide together. Let's see if I can do an instant replay. There we go. So here they're apart, together, and way too close together. As it's the middle of the quarter. Nothing personal. All right, I got another question for you. Why is the bond energy of H2 greater than the bond energy of Cl2?
What was bond energy again?
Because it's smaller. Very good. That is correct. Coulomb's law is smaller, closer together. Since it is closer together, it requires more energy to separate it out. These are further apart, and they've got electron sharing going on, a little bit of repulsion. It's easier to separate them out. So those are a few of the reasons. More reasons would include H2 is like helium. That's another reason why, but the distance is the main reason. All right, we will see you tomorrow